Hey everyone, welcome to Cal 2. I hope you find it riveting. Lots of fun times to be had, lots of gratifying detective work to play. Now, a large chunk of the essence of Cal 2 is all about asking the main question of Cal 1, but in reverse. If you recall in Cal 1, the main question was, hey, here's a particular function, what is its derivative? However, now for Cal 2, the question gets inverted. Now it's, hey, here's a particular function, the derivative of what other function yields this particular function? That brings us to the idea of an antiderivative. The notation for an antiderivative is a capital F, like so, and it is defined to be any function whose derivative is lowercase f. So that's what I'm writing here. Let's say an antiderivative of lowercase f is any function at all, whose derivative is lowercase f. Is lowercase f. Good. And express the same thing more tersely mathematically as saying capital F is an antiderivative of lowercase f. If and only if, that's this double-headed arrow here, f prime, capital F prime, is equal to lowercase f. So let's look at an example. Let's ask the inverted question for this guy. Find an antiderivative of lowercase f. Say it's something simple. Let's say it equals 2x. Now let's ask the inverted question. The derivative of what function gives us 2x? Well, x squared certainly fits the bill. The derivative of x squared is certainly 2x, but crucially, it is not the only function that fits the bill. X squared plus 100 fits the bill. X squared minus pi fits the bill, and so on and so on and so forth forever. Infinitely many functions fit the bill. The derivative of all these guys in wild cherry red here, in all cases, is 2x. And this is precisely why we phrase it as a antiderivative of lowercase f rather than the antiderivative. It highlights a huge difference between Cal 1 and Cal 2. A differentiable function only has one derivative, but if a function has an antiderivative, then it has infinitely many. Now, how do we more compactly express the fact that lowercase f has infinitely many antiderivatives? Well, that brings us to this fancy fellow right here. We take lowercase f, we draw a fancy stretched out s to the left of it, write a dx to the right of it, and term the entire expression the indefinite integral of lowercase f. It stands for the entire infinitely large family of antiderivatives of lowercase f. So, entire family of antiderivatives of lowercase f. For instance, in building off the previous example, the entire family of antiderivatives of 2x is written as x squared plus c, where c is understood to stand for any real number. And it's that plus c that serves to indicate that 2x has infinitely many antiderivatives. Without that arbitrary c, we'd have an x squared by itself, which is just one antiderivative. Now, let us go ahead and invert many of the derivative rules we learned in Cal 1. Let us start with trig. This fellow is going to be a negative cosine of x plus c. Likewise, integrating cosine gives us a positive sine of x plus c. Going down the list, integrating secant squared, that is going to give us a positive tangent of x plus c. And notice as I go down the list that the derivatives of the expressions on the right equal the corresponding insides of the indefinite integrals on the left. Integrating secant tangent, that will yield a positive secant of x plus c. Okay, that's a seriously ugly c. I'll give him some plastic surgery here in a bit. But for now, let's finish off the trig. How about integrating cosecant cotangent? That's going to be not positive cosecant, but negative cosecant of x plus c. And helping out our friend here, tidying him up. There we go. Good c, lovely. And that's it for trig. How about e to the x? How about our transcendentals? Well, integrating e to the x is going to be e to the x plus c, naturally. And what about stuff like this? How about stuff like this? Dx over x, trick for that is to rewrite it as 1 over x dx. And the derivative of the natural log of the absolute value of x is 1 over x, so that is our antiderivative on the right. Likewise, for this more complicated one, I can rewrite that as 1 over the square root of 1 minus x squared dx. And that inside is the derivative of anything that fits the form of inverse sine of x plus c. And we can go on and on and on like this for all the derivative rules we learned. Remember, the derivative of the right side has to equal the function inside our integral on the left. And incidentally, this gives us a great way of checking to see whether we've done an integration problem correctly. And remember, it is that plus c. That plus c is what indicates that our functions inside the integrals have infinitely many antiderivatives as opposed to just one. Now then, properties. Properties. It is high time we address some integration properties. Here are a few of them. The first is going to be our power rule for integration. So, the indefinite integral of x to the n, that is always going to be x to the n plus 1 divided by n plus 1 plus c, so long as n does not equal negative 1. If n equals negative 1, that creates division by 0 on the right side. Second rule, just like for derivatives, we can yank constants out of integrals. Like so. The golden k on the inside becomes the golden k on the outside. Thirdly, again, just like for derivatives, we can break apart large integrals into smaller integrals so long as the main operations going on the inside are addition and or subtraction. We cannot do this if the main operations are multiplication and or division. Next, well, as for why these rules are true, well, let's prove number 1, the power rule. For this little fella, all we got to do to prove this is to take the derivative of the right side and verify that it equals x to the n, the function inside the integral. Well, for the derivative power rule, all I have to do is bring down the exponent and subtract 1. So, n plus 1 minus 1, that's for my x term. And of course, the derivative of a constant c is just 0. So the n plus 1s, they kill each other off. And I get x to the n, all in all. For example, integral of x to the 5th gives me a 6 up top as an exponent, 6 downstairs as a denominator. And I can do that with any real number. Let's say pi. Pi plus 1 up top, pi plus 1 downstairs, plus c in all cases. Again, remember, this formula does not work if n equals negative 1, because that creates a division by 0 on the right side. But if n equals negative 1, then the indefinite integral is just the natural log of the absolute value of c, or absolute value of x, plus c, since x to the negative 1 is 1 over x. Now then, why is number 2 true? Let's illustrate that with an example. A second ago, we showed that this integral in blue equaled x squared plus c. How does the integral in blue compare to this new expression in red, where the only visual difference is that the 2 is outside the integral? Well, let's see. X is x to the first, and applying the power rule on that fellow gives me this right here. Subsequently, I distribute the 2 to get this right here, and hey, 2 times some arbitrary constant c1 is just another arbitrary constant, so we might as well call it the same capital C as the one in blue. Thus, the right sides match, and we can conclude that the integral in blue does in fact equal the expression in red, justifying that we can in fact pull out constants from integrals without having the value of the integral change. And finally, to illustrate number 3, suppose I want to integrate this guy. How about we let him be, start him off with an exponent, an x to the 4th, and then we have a 3x, and to that we're going to add an e to the x, and to that we're going to add a sine x, and to that we'll subtract a root x, and cap it off with a 9. Number 3 says that I can do the integration piece by piece. For the first piece, I can apply the power rule. The second piece, the trick is to rewrite the x as x to the first and apply the power rule again. 3 comes along for the ride since it's just a constant. E of the x, of course, yields e of the x. Sine yields a negative cosine. Oh, we encounter a wild square root, but well, it's not so wild. The trick is to rewrite roots as powers and apply the power rule. And finally, last piece, the integral of 9. Well, if it's not clear what to do with just a plain number, a quick trick is just to rewrite that number as 9 times x to the 0, in this case, and apply the handy-dandy power rule. Once again, to reiterate, the 9 is just a multiplicative constant and comes along for the ride. Now really, I just need to simplify those last 2 terms. Dividing by 3/2 in this fellow here is the same as multiplying by 2/3. And of course the last term is 9x, and I cannot forget my plus c's. Remember, do not forget the plus c. Without it, it's not an infinite family. It's just a family of one, which is quite lonely. Anyway, in a nutshell, those are the three of the most common integration techniques that we'll use on bigger integrals. Power rule, pulling out constants, and doing integration piece by piece, so long as the main operation going on the inside are addition and or subtraction. Now, oftentimes, unlike the last problem I did, and especially in the coming weeks, it will not be immediately obvious how to do an integral. Consider this guy here, the integral of e to the pi x. For a first stab at this, you might think, oh well, how about e to the pi x plus c? But that does not work, because chain ruling e to the pi x gives pi e to the pi x, whereas the inside of the integral is just 1 e to the pi x. However, I will get e to the pi x on the right side of this equation if I multiply both sides by 1 over pi. And the benefit of doing that is that I know I am allowed to move constants in and out of derivatives, and that tells us exactly what we need to take the derivative of in order to get just 1 e to the pi x. So all in all, I'm just going to stick a 1 over pi on the right side here, and that is the indefinite integral of e to the pi x. A similar story is going to hold true for some trig function like so. It is not a sine of plane x, it is a sine of 3x, so the entire family of antiderivatives is not negative cosine of 3x plus c, but rather negative 1/3 cosine of 3x plus c. To take another example, what if we wander into even more unfamiliar territory, like the integral of 4 to the x? How should we tackle something like this in a similar fashion? Well, when in doubt, it never hurts to write out a nice derivative formula. The derivative of a to the x is always going to be a to the x times the natural log of a whenever a is positive. And if I want just a to the x on the right side, I need to multiply both sides by 1 over the natural log. And patterning off the previous example, I can migrate that 1 over the natural log into the derivative. In the problem below, a is equal to 4, so if I want the derivative to be 4 to the x, I need to take the derivative of some member of this family of antiderivatives on the right. And again, if we want to make sure that we got it right, we can simply take the derivative of our answer and see if it equals the function inside the integral. It's a foolproof way of checking our answers. Now, I want to slow down a bit here with a conceptual segue, and it comes in the form of a question, and you may have been asking yourself this already. Why in the world have we been using this for the symbol for integration? Why not simply the long, stretched out squiggly s? For that matter, why not a happy face? Why not happy face of 2x equals x squared plus c? Okay, but more seriously, what's really confusing, or what tends to be confusing, is the seemingly random inclusion of the dx. Because dx has a geometric meaning from Cal 1. Back in Cal 1, when we took the derivative of this guy, we could express it, of course, as f prime, but we could have also expressed it as dy over dx, and so could have written the derivative definition like so. And of course, the right side here is the instantaneous slope. What gives dy over dx geometric meaning is that it stands for rise over run. dy and dx mean the infinitesimally small changes in the y and the x coordinates, and their ratio, which is the instantaneous slope, will be different at different points on the graph of y equals f of x. By the way, in upper level math and physics, dy and dx are often called differential lengths, so they do have geometric meaning. So I'll write that out here. dy and dx have geometric meaning. To illustrate that meaning, suppose we have a nice standard parabola. Let's try that again. Nice standard parabola, and we want to find the instantaneous slope at a point. Pick a nice point like 3, 9. Of course, the derivative is 2 times the x-coordinate of that point. And so the slope is going to be equal, instantaneous slope is going to be equal to 6. But what that number means in terms of differential lengths is that at that specific point, their ratio, so to speak, is 6. At a different point, say the vertex 0, 0, the ratio would be 0, since 2 times 0 is 0. So what's the rationale for putting an entity with geometric meaning into our symbol for integration? What's the justification for doing something so seemingly random? We'll talk about that fully in a future video, but for now, if the dx seems random and is causing you any conceptual confusion, just note for now that it's justified. There is a good reason for why it's part of the integration symbolism. And also, please don't write this on quizzes and tests. Your present and future instructors might become a little bit cross with you. So, yeah, just bear that in mind. Bear that in mind. Now, let's look more at integrals in light of the fact that the presence of that dx, that infinitesimally small change in x, is justified. If its presence is justified, then a really neat technique emerges for puzzling through more tricky integration problems. That technique is called U-substitution, and for now we're just going to preview it. I'll devote a future video solely to this technique, so you don't need to worry about mastering it right now. So we're just going to preview. How about we take a stab at that previous integration problem, the one involving an e to the pi x, but this time around let's do it with U-substitution. The way this technique works is that you want to look at the function inside the integral and select a piece of it to be the letter u, to be the variable u. How about we select that entire exponent, the pi x? With that selection, u is a function of x, it's equal to pi x, and this allows us to take the derivative of u with respect to x. But let's intentionally express the derivative in differential notation, du over dx, and if that's our derivative, then the way du and dx relate to each other has to be like so. Du equals pi times dx, and loosely speaking, you can think of the dx as coming over to the right side. Furthermore, let's denote u with a red star and du with a blue star. Therefore, the red box is u, and now the goal is to somehow stick du inside the integral. But there's now pi x and dx in the original integral, it's just e to the pi x dx. So how can we transplant du inside the integral? Well, you see it here. We're going to rewrite 1 in a very clever way, pi over pi, and now we get what we want. We can pick out our du, indeed we can. Here it is in blue. And watch what happens next. The original integral expressed completely in terms of x and dx can be expressed completely in terms of u and du. We have a nice simple integral in terms of u, and finally throw back in u as a function of x. And there is your answer. In a very symmetrical nutshell, that is how U-substitution works. Now then, you may be thinking to yourself, well, that integral was pretty easy to begin with. Why on earth do I need to learn this new convoluted way of doing things? Well, let me tell you, some integrals ain't going to be that easy. Some, like this one, are going to be really aesthetically unappealing. You ain't going to want to look at them, and U-substitution is what's going to come to the rescue. Let's let u be the nasty thing, the natural log. The derivative, of course, is 1 over x. I'm going to migrate that dx to the right side to relate the differentials du and dx. As before, I will star the u in red and box it in red as well. And I'll star the du blue. And look, here is the du in this blue Tetris looking shape. Furthermore, notice the shape in blue is over the shape in red, which means this entire unsightly integral reduces to a nice, clean, crisp du over u, which can be rewritten as 1 over u. And of course, that integral is a nice natural log of the absolute value of u. And finally, toss back in your u as a function of x. U is the natural log of x. And if you don't believe this is the right answer, well, sir or madam, you can always check. Just take the derivative of your answer. Let's remind ourselves that the derivative of plain old natural log up here, plain old natural log of the absolute value of x is always going to be 1 over x. So then chain ruling that first term in the brackets gives us 1 over the natural log of x times 1 over x plus 0. Derivative of c is 0. And of course, this exactly matches what we have on the inside of our original integral. Now, for both of these problems, this one and the previous, the choice of u was a choice left to us. And choosing the right kind of U comes with practice, so I'll talk more about the choosing process in the full-blown U sub video in the future. However, notice also that conceptually, U substitution completely depends on the presence of the dx inside the integral being completely justified. That presence needs to be justified. As soon as I took the derivative of U with respect to x, I introduced the differential lengths du and dx, and I solved for one in terms of the other. It was a fully geometric argument, which means that at some point we need to justify the presence of that geometric term, the dx, in our notation for integration. And again, that'll be looked at fully in a future video. How about we radically shift gears and talk about some applications now to physics? And, man, what's with the random brown hue in the background? Yeah, let's roll with it. Could be fun. So, some applications. Here in purple are 3 standard concepts in mechanics: position, velocity, and acceleration. In Cal 1, we learned how to mathematically go from top to bottom. Purple and gold, colors of royalty. The derivative of the position function with respect to time is always going to be the velocity function, and the derivative of the velocity function with respect to time is going to be the acceleration function. And yes, you have guessed correctly, the way to go from bottom to top is through integration. Integrating acceleration with respect to time gives you a velocity, and integrating velocity with respect to time gives you position. But, big but, there's one major caveat with this bottom to top integration process, and that's best illustrated with an example. So let me change to a better green here. Suppose we have an object moving with a constant velocity of, let's say, 3 feet per second. And the caveat is this: there are infinitely many position functions that are compatible with a velocity function of a constant 3 feet per second. Any position function of the form 3t plus c, which we obtain through integration, anything of the form 3t plus c has a velocity of 3 feet per second. So this information, just this information in green up here about velocity, isn't practically useful in moving up the golden arrow from velocity to position. If we're trying to describe the position of an object in the real world, we want it to have just one position function, not infinitely many. So to illustrate this from a more physics perspective, let's look at what I'm drawing down here. Now, if you've already taken mechanics or are going to take mechanics, remember that there are 2 points in space that you need to pick out in order to coherently define a position function. That's a reference point, which I've indicated in white with the dashes, and all individual positions are measured with respect to a chosen reference point. And also a starting point, which I'll indicate with blue. The starting point is just the point where you, the observer, have chosen to start your stopwatch in observing this moving object. So for this first example, the starting point and the reference point are at the same place, so the position function is 3t. When t is 0, s is 0. However, suppose we start our stopwatch when the object is 7 feet to the right, and let's say right's the positive direction. Well, in that case, our position function is 3t plus 7. If you throw in t equals 0, you get the starting position being positive 7 to the right. Likewise, 7 to the left, if we start our stopwatch when the object is there, the position function is 3t minus 7. Again, t equals 0, throw it in, negative 7. So let's put some more information to the stuff in green up top. Let's suppose s of 2 is 4. At the timestamp t equals 2, the object is positive 4 feet to the right. This allows us to solve for c. It allows us to solve for one particular position function. Just throw in 2 for t, so s of 2 is 4. S of 2 is also 3 times 2 plus c. And now we can solve for the appropriate capital C, which will give us one position function. All in all, our position function is 3t minus 2, and that is all there is to it. So when I go up the golden arrows from one function to another, I need some numerical information about the function that I'm going to. If I'm going from v to s, I need some numerical information about s. Moving on to the next order of physics business, how about we prove a famous physics equation? If you've taken mechanics or are going to take mechanics, you will see this equation and it will be one of your best friends or one of your most menacing enemies. And it goes like this. If we have an object that's moving linearly, which means along a straight line, with a constant acceleration, in other words, acceleration is a fixed number, then what this equation right here is saying is that delta x, the change in position from some starting point to some other point in space, is always going to be the starting velocity times the time it took to get to that second point, plus 1/2 times the constant acceleration times the amount of time squared, t squared. In other words, delta x is v initial t plus 1/2 at squared. So a pretty bizarre looking equation. From whence cometh it? Rest assured, big things have small beginnings, so let's begin with a simple equation. Again, assuming constant acceleration, the velocity of this object at any point in time is going to be its starting velocity plus the constant acceleration times the time. Now this is a very intuitive equation. For example, suppose you're driving your fancy schmancy car down the highway and your foot is pressing on the pedal in just such a way that the velocity of the car is increasing at a constant rate of 3 feet per second every second. For example, if I, standing on the side of the road, start observing you right when you're going 70 feet per second, then 1 second later you're going 73, 70 plus 3. 2 seconds later, you're going 76. In other words, 70 plus 2 times 3. 3 seconds later, 79. In other words, 70 plus 3 times 3, and so on and so forth. And that is all this equation is saying. And once we have this equation in hand, it's high time to calculus it. I know that if an object has this velocity profile, then a position function for this object has to fit the form of an indefinite integral. Well, after substituting, we get this. After breaking it apart into 2 integrals, we get this. And A and V are constant. I can yank them on out. And this leaves me with this. And where did that Phantom 2 come from? You are bizarre, Phantom 2. Erase, erase, erase. T is t to the first power. There's an understood 1 inside this first integral. In other words, t to the 0. From here, we simply fall back on our handy-dandy power rule and get v initial t plus a times 1/2 t squared plus c, which I can refashion like so. That is my position at any point in time. But what do I do with that pesky capital C? How can we get rid of it? Well, by definition, x of 0 is the starting position, the position at t equals 0, when we started our stopwatch. And now with this equation down here, we know that x of 0 has to be 0 plus c, which means the starting position is our c value. Finally, x of t is v initial t plus 1/2 at squared plus x initial. And finally, so I lied the first time. Finally, the difference in the positions is v initial t plus 1/2 at squared, which we can crisply compress like so. So, a very crucial formula in introductory mechanics. Looks a little bizarre, but calculus swoops in to demystify it. Okay, it's final boss time. How about we end in familiar territory by slightly increasing the computational difficulty level of something we've done before. Suppose we have an object moving solely on the x-axis with a certain velocity profile. Let's have it be something kind of prickly. Let's let the velocity be a trig function with some polynomial tossed in at the end. Suppose also that this object begins moving at the point 3, 0. With that in mind, what is the x-coordinate of this object at the instant t equals pi over 4? Well, here we have it here, t equals pi over 4. Well, first thing I want to do is I want to migrate up. I want to go from a velocity to a position. So whatever this particular position function looks like, it has to fit the form of the indefinite integral of velocity. And chugging that guy out, that gives me a -1/4 cosine of 4t. Second term is t to the 4th over 4 plus c. Whatever my particular s of t is, it needs to fit that form. Now it's high time to throw in my numerical information. I know this guy begins at 3, 0. Begins means t equals 0. I'm interested in the x-coordinate. So, s of 0 is 3. S of 0 is also -1/4 cosine of 0 minus 0 to the 4th over 4 plus c. And this enables me to solve for c. C as a mixed fraction is 3 1/4. As an improper fraction, that's 13/4. I toss that bad boy in to my position function, and I get S of t is equal to the same thing as before, but plus 13/4. Now, for most problems, you'd be done, but this problem wants us to go one step further. I want to find S of pi over 4. I want to find that x coordinate. What do? I throw in pi over 4. That comes out to be this stuff here. Cosine of pi is a -1, of course. And first term, positive 1/4. I'm going to put that 13/4 right next to the 1/4 and leave the oddball term out to the right, pi to the 4th over 4/5. Those first two terms combined get 14/4. 14/4 simplifies to 7/2. Pi over 4 stays as is. And 4 to the 5th is 4 to the 4th, which is 256, times 4, which is 1024. That is how the cookie crumbled for this problem. So, quite a computational doozy, but I want you to keep the bigger conceptual questions in mind. Why the dt's? Why is dt in our integration symbolism? Why the dx's? What's the justification for incorporating these geometric quantities into the integration symbolism? It's all too easy to go through courses like Cal 2 without stubbornly thinking about exactly why all the conceptual details make sense. And most eventually just resort to doing mindless computations, but I want you guys to think stubbornly about why all those conceptual details make sense, because that is when the subject becomes rewarding and a lot of fun to learn. A lot of fun times we had in Cal 2, and there's also a pure and simple sort of fun in drawing that squiggly S. Just keep drawing it randomly a few times, and you'll feel like you've joined a small, super secret society of human beings who understand what all these weird, fancy calculus symbols mean.